String theory grew out of a number of different puzzles that were around in sort of the middle of the 20th century. So the two pillars of the 20th century in terms of physical theories that came out are Einstein's relativity and also the theory of quantum mechanics. And these are fundamental things we learned about nature in the 20th century. And our entire technology is based on so much of those discoveries. But one of the things you find is actually fundamentally they're incompatible. When you try and cast the theory of gravity, a fully relativistic theory that Einstein gave us in 1915, when you try and cast that as a quantum mechanical theory using the, if you like, traditional techniques, it just doesn't work. And so one of the things that people were trying to understand in the 20th century was, what is the theory of quantum gravity? Because it's very important, not just as an esoteric question, but because our universe at some very early stage really relied on that physics, and we don't know what that physics is. So that really is one of the sort of backdrops for why people started working on things like string theory. And string theory emerged as one of these theories that managed to give you an idea, a possibility, a possible mechanism for how these questions could be answered. And one of its greatest triumphs is that it actually does give you a theory that puts together gravity and quantum mechanics. So it gives you a theory of quantum gravity. Now, one of the things we're still wondering about is whether that is the theory of quantum gravity, the one that nature actually uses. So what is it, you're probably wondering? Why does it work so well? And one of the things it does, it actually sidesteps one of the cul-de-sacs we got into in particle theory, which is treating everything as point particles. And instead it says, well, instead of just there being points, little fundamental points perhaps which interact together in various ways, you can also have, take a point and stretch it out and get a string-like object, a one-dimensional object. And then that object, in addition to maybe being very small and looking like a point, also has that internal structure of being sort of stretched out. And so it can actually vibrate like a string would, say a string on a musical instrument. And then one of the really beautiful ideas about string theory is that it can give you many, many different kinds of particles which are really just different vibrations of that same string. Just like on a guitar string, you can play lots of different notes. It's all the same guitar string, just vibrating differently. And so it has a beautiful sort of economy of how it incorporates some of the physics that it's trying to describe. And we still don't know whether it works yet, but one of the really great successes is that you can see immediately that it has enough structure within it to contain all of the particle physics we already understand from work in the 20th century. Even though we don't know whether string theory is going to help us solve a lot of these various questions that have come up in particle physics and the origins of the universe, etc., one of the things we've had already great success in is understanding black holes at the quantum level. And this goes back to some of the issues that Stephen Hawking worked on in the early 70s when he discovered Hawking radiation. He basically put together quantum mechanics and relativity, but in the context of black holes, which are solutions of Einstein's relativity. And what he found, although he didn't have a full theory of quantum gravity, he was able to at least see this important effect that black holes actually radiate, and they have an important quantum property which you don't see if you don't include quantum mechanics. And they predict all kinds of interesting properties that black holes should have. They should, for example, evaporate and interact with each other in various ways that are sort of important. And so one of the things that string theory was able to do, because it supplies a full theory of quantum gravity, is it allows you to study black holes in that context. So we use the equations from that part of string theory to study black holes. And we were able to really continue some of that work Hawking began and really complete it and understand a lot about the structure of black holes, how they behave at the basic quantum level, and apply some of those ideas to a range of other problems in string theory now. So that's been one success we can sort of hold up so far.